So let's dive into exactly what we're looking at. I won't go into what the model is because it's not terribly pertinent. The idea here is that once you have a model built, you need to get it into some sort of a streaming solution. And if you can do stream, you can do micro batch and batch as well. So I'm going to go for the hardest one. And the problem space we were in is that we have to read in data, do feature engineering on it, do in-memory data joins, model serving, and data stewardship, all with about 5 nines availability, and all within about 10 milliseconds, give or take, from the time that we receive it to the time that we emit it again, which is pretty quick by a lot of standards. And we also have to have support for a couple of different processes, including analysts looking at this data set, and exactly once message processing, because the thing upstream from us kind of has issues if we don't respond within time or respond more than once. Cool. So now that we have the idea down, let's kind of go through exactly what each of those means. And this is very high level. I know some of you are probably going to be bored. But with feature engineering, the idea here is simple features. So basically, simple algebra. If you divide 2 things, add 2 things, multiply 2 things. Historical aggregates, which you can think about as combining different observations. So if I'm really interested in, for example, my email, and I want to see how many messages I receive, I can look at average number of messages a day on the 30, 60, 90-day period, or 30, 60, 90-second period even. And also batch compute features, which are some really interesting submodels that we've created that sit underneath everything. And because of data requirements or something else, we actually compute them sort of in a Lambda architecture off to the side. And then we'll serve them up through in-memory data stores. So it's sort of a key value where you give the memory store a key, and then it'll give you back the correct value without having to compute everything on the fly. And there's also in-memory data joins, so not necessarily all the information we get in the stream is what we need, so we might need to add further tables. And so we've set up a very cool system where you can do in-memory joins and have that data ready to pull in. And this gets a bit difficult once you start thinking about things like null handling and fuzzy matching and sort of named entity recognition on the fly, which is fun to look at. And finally, the kind of interesting part to everybody here is model serving. So once we have this vector that we've created, we have to make it H2O consumable, which is pretty cool because they've, with the Pojo, included an API that will unfold it and create an array of doubles, which is what H2O takes in, and go ahead and score it for you. And the scoring itself is actually really quick. So we're running on boosted trees, which you can measure like in microseconds almost, because it's all if-else logic. So it's really, really fast. And then once we have a score back, or many scores, depending on if we're running an ensemble or submodels, we need to add that into the vector. And then finally, get the clicker to work. Yep. Data stewardship, which is just adding the data that we have back into the authorization. And so as I mentioned, we've got about 10 milliseconds for all of this to happen. And this is, of course, with data stewardship, sending the message back to the source that gave it to us, providing a live copy to analysts, so sort of a Kafka stream, and then serializing it for future use so that we can be the system of record. And this kind of builds out quite a lot of very different requirements for a stack that we need to create. We need to be able to talk to many different sources and send to other different sources, to do some math within it, to get the features that we like it, have an in-memory database so that we can call to other things and bring information in, and of course play well with the rest of the ecosystem and play well with H2O where we're doing our model building. And it's actually kind of difficult. So we looked at a couple of different solutions. I'm not going to spend too much time on all of these, but once you get the H2O object, it's all about sort of integrating. And I know H2O also has some solutions, but this is really to get down into very, very low latency, high availability needs. There are, of course, commercial offerings. I won't go down the full list, but there are many, many people who are willing to take your money from you and go ahead and build something. But if you're at this conference, you're probably the people building something, not the people paying money for other things. There's also Apache Spark, a really, really great project that's very well supported and has a very large community. But unfortunately, because of the way that they do micro batch and batch, it's hard to get observations in and out in under a second. You can get, on average, in the millisecond range. But the first message that received might be waiting for the rest of the batch to come in, and so you get this weird sort of delay. And it's not actually a true stream. It's just doing these little batches. Apache Storm gets around that issue. They actually do streaming pretty well, and they have great availability bits and all of that. But unfortunately, there's kind of an issue where if you need high availability, if their name node Nimbus goes down, or name node equivalent, then you can be sitting without a system for about a second, which leads to the requirement to have multiple systems sitting in parallel, and you either wait for a quorum or for other systems to respond, which isn't really great. There's also Apache Flink, another really great project. Fortunately, it's pretty young, and their enterprise readiness is kind of a goal that they're aiming for, but they're not quite there yet. There's not many folks who use them in prod, but it's a really cool project to watch out for in a year or two. And finally, Apache Apex, which is the solution that we've gone with. And the cool thing here is Apex actually has a really, really old code base. It was a commercial offering under DataTorrent. It's used in thousands of nodes at a couple of different companies in production for very low latency requirements. But they've actually taken this commercial offering and open sourced it last year. And because of this, we were able to get involved and identify that it met sort of all of our requirements for availability, and they had a lot of other cool features that would build in really well. And because of the POJO object that H2O spits out and the fact that Apex is primarily designed to be used in Java, there's a really easy integration point there. And as an added bonus, Apex kind of comes with an in-memory data store and plays well with many, many in-memory data stores like Redis and things like that. And so this is actually going to wrap it up really quickly. And I just wanted to leave, it's a lightning talk, I know, leave a little bit of time for questions, just in case you guys were interested in any bits of this, because I know it's a very high-level overview. But thanks.
Thank you. If you have any questions, happy to walk around. Yeah, thanks.
What's the solution you use for joining with the logistic data, the remaining data that is now available?
Yeah, so the solution there is make it be in memory. You can actually subset depending on how you want to do the joins. There's no easily generalizable way that I've seen. Redis has some support, but not quite. And so the idea is to basically have a key and a value, and the key is some unique hash of the observation coming in that contains the data that you want. So if you only want one or two fields, you can hash on those fields. If you're joining on 1, 2, or 3 fields. And then in your in-memory data store, you can have the key be the hash of those, and the value be a list of the other observations that you'll need or the data that you'll need to compute. So if you want to look at, like, assuming that I was Gmail for a second, the average number of emails that I receive, the key would be something like the hash of my unique identity to Gmail, and the value would be the list of emails that I've received within different periods that are well bucketed, so that you can just do an aggregate on those and look at like the average flux or something like that. Does that get at the question?
So you use Redis server?
We're not actually. We're evaluating a couple of different in-memory options. So we've looked at Redis, and there's a couple of others that we're really interested in, but it's a bit early for me to say which one is the best or not.
Anyone else?
Cool. Oh, one more.
What if the data is too big to be held in memory to be joined?
That is a great question. You make it not too big. So, like if you're willing to really spend a lot of money, you can get on the order of a terabyte or two on an actual, on one machine. If you're going for the largest number of slots and the biggest cards per slot, you can work sort of around that. But generally, you don't need to look at the whole data set to do a join or to do a roll-up. You just need the information for particular accounts or IDs or something like that. So if you partition it well enough, you can guarantee that these accounts will only ever hit this box, so we have the join data in that box. And so you can subset so that the data will fit, hopefully. If you can't, then I'm sure you can spend a lot of money on very, very fast SSDs and hope that your latency requirements aren't that bad. Cool. Any other questions? Serialization is slow. So that is a great question. We're working off of a couple of available databases. So serialization, as far as we see it, is really just hashing the keys that we're interested in. There's some serialization that happens underneath. Is that kind of what you're asking about?
Yeah, I was just wondering what your strategy was for how they play together.
Yeah, so the plan there is really just subset key value lookup. And key value lookup from local machine in memory is really, really quick. And there's some interesting offerings for tiered storage, like Alluxio is one thing that we're looking at out of AmpLab Berkeley. And that'll give you kind of varying levels of SLAs, but because of the high need there, it's all in memory, and just subset it down or make a requirement that you can fit all of the observations for a particular account or something like that onto one machine. And then there's a lot of very, very interesting optimizations that happen underneath the hood, and unfortunately that's not really my specialty. I think I can chat about it a little bit, but I don't want to say anything foolish, so. Cool. Oh, thanks.
Thank you, everyone. Thank you for